So this question is a little tricky. You're trying to investigate the global conditioning of interpolation. We already know a little bit about how equal space points are not great for interpolation. This is just another way to kind of get the exact same thing. In fact, you'll see a little bit later, you're actually going to find Lebesgue constants in terms of linear algebra constructs. So this first question, we have to construct something that maps. That's what this is trying to get at. So you have two sets of points, and these are just, dependent variables. So xj and yj, they're just two sets of equal space points. Okay? Yj's in this case are not evaluations of the data. That's one important thing. To answer this question, you need to construct something that has a polynomial interpolant of xj and some function f, just some function. The point pairs are going to be the xj's and f of xj. That's good. One of the interpolants. The second interpolant that you're going to construct is this thing. So in this case, this is going to be the interpolant of these points evaluated at a new set of points. So instead of f in this case, you can get this. Yeah. So this set of points is going to be from F. This set of points is going to be from P from this set of pair. So from those two things, you can construct this matrix A. So it's really mapping the xi's and the yi's to these two things. So just think about how you create a polynomial interpolant using matrices. The van der Maan matrix is a simple way to do that. So this thing is going to have a few van der Maan matrices inside there. So just write down what you know, how you go and map these points to a polynomial interpolant, and how you would write down these points as a polynomial interpolant, and then think about what the similarity between these two things are. And that should give you an idea of what this mapping looks like. Okay? And you'll use that mapping later on in the question. Okay? Does that help, hopefully? I think this is usually the sticking point for this question, is understanding what in the world you're doing with these things, because it's hard to actually write that down a bit. So, any other questions for the homework? All right. So, I unfortunately slipped and fell this weekend and cracked my laptop screen. So I think everything's working, but we're going to find out very soon whether that's actually true. Okay, so we left off, yeah.
Are you publishing a final review?
Yes, I will give that out actually probably before. I'll try to get it out by Thursday, so you have some time with it. Yeah, and the solutions will be available by that time. There is one little thing is that because the last homework, let's see. Oh, no, I'll put out the solutions by the time the final exam is available, so that's not an issue. Okay, so we left off talking a little bit more about finding eigenvalues and how we're going to do that computationally. So we brought up this idea of similarity transformations. Similarity transformations are simply transformations that take A and then transform it with x inverse and x. Okay, so whatever those things are, that's the transformation. Okay, that new matrix has the property that it has the same eigenvalues structure as the original matrix A. So the idea here is really, let's come up with some clever transformations such that when we do this to the matrix A, we get back out a matrix that's easier to find the eigenvalues of. So for instance, it's really easy to find eigenvalues of a triangular matrix because we know the eigenvalues are along the diagonal. All right? That's really the goal. We want to get an upper triangular matrix so we can read off the eigenvalues on the diagonal. I was supposed to show this, but this is how we're going to do it. We're going to use what's called a Schur factorization. So x inverse x, whatever those are, they do exist for various cases. We talked a little bit about that. every matrix has a sure factorization. So this is really where we're going with it. And the nice thing here is that, in fact, these Q's are going to be unitary or orthonormal, so our favorite matrices Q. They are not necessarily going to be the same matrices we had before. It just happens that these happen to be unitary. But we know that this is actually in the form of an inverse, a similarity transformation, because we know the normal matrices inverse is its conjugate transpose. So that's why this says actually the same thing as a similarity transformation, only flipped. So A is being, both matrices are being taken to the other thing. And then we can say, well, this T is going to have the special property that it's upper triangular. So therefore has the eigenvalues we want. So that's why we're doing this. And this is what we want to construct. So a lot of this is going to be about how we do that. Let's skip ahead a little bit here. Oh, so this also, these kind of three facts are also kind of important here. The eigen decomposition is a similarity transformation because you see, well, this eigenvalue matrix here just has a diagonal, and of course that has the eigenvalues on it. So that is a special case of the sure factorization. There's one where there's just a unitary transformation. So for special A, again, you're going to get a diagonal matrix here. It just so happens to work. But we always have a sure factorization. So for whatever reason, we want to get something that's in that form. Sometimes it's a little easier than others. Okay. That was weird. There we go. Okay, so before we kind of embark on the more computational side of things, it is important to kind of consider the condition number. We saw how this comes into play for AX equals B, and here we want to think about how this happens for a simple eigenvalue. Simple eigenvalue means that it has multiplicity of 1, so it's not a repeated eigenvalue. It has nicely defined eigenvectors, okay? So there's two types of eigenvectors we're going to need. One is the normal eigenvector, the right eigenvector, and the other one is the left eigenvector. So this is another set of eigenvectors. It just happens to be on the other side, hence left. We actually are going to use the property that y times x, so this is an inner product or a dot product, cannot be equal to 0. Okay? So the right and left eigenvectors for a simple eigenvalue can never co-align, is really what that's talking about. They have to be somehow an angle between them. Okay? And we'll see why that's important here too. It's not that you can't do this exact same analysis for non-simple eigenvalues, but that would be lectures, and I don't think we want to spend that much time on this, but to realize that there is something for more complex situations. Okay, so we're going to do the same thing we did before. We're going to perturb A, and we're going to perturb X and lambda. So we're perturbing lots of things. And we're interested in what's going to happen to these things when we look at these more complex things. And so we're just multiplying things out. We know that A times X is going to give us lambda times X. So we can use a bunch of this stuff and cancel it out from both sides, which means we have something a little bit simpler where we have the delta A times X, A delta X, delta lambda X plus lambda delta X. And then we're going to multiply by the left eigenvector on both sides. So there you see, okay, well, I know what this thing is going to be. I can use lots of different identities. And I can, again, actually simplify this down. So I have y star delta AX and y star delta lambda X. Okay, so I've gotten rid of basically all of the deltas on the x's and y's, all the eigenvectors. And then I can solve for delta lambda based on delta A. So if I perturb A, it's going to perturb the eigenvalue a little bit. Now, the statement is just basically saying if A changes a little bit, then the eigenvalue is going to change a little bit, except based on what basically y star x on either side of this thing is doing, but even more importantly, this. So we can see if this was close to 0, this is going to blow up. So the condition number is going to actually blow up in that case. So it's actually, the condition number is predicated on how collinear the eigenvectors are. That is a geometry question. There's reasons for this. If we had these being collinear, that would mean we'd actually have a non-single simple eigenvalue, and the problem gets a lot harder in that case, as we're looking for spaces, not just single vectors, or single-dimensional spaces in that case. Okay. So that's the short end of finding condition numbers for simple eigenvalues. Again, you can complicate this quite a bit, especially for complex spaces or large eigenspaces. But this is basically the takeaway. The eigenvectors actually determine how the mapping between delta A and delta lambda occur. And that's how we end up defining the condition number. All right. So talked about the condition number. We know how hard the problem is now. We have some idea how to compute that or determine that. Now we want to compute the eigenvalues. Eventually we wanted to do that. And here's where our relationship to finding roots of polynomials comes in. There is a theorem that states that for m greater than or equal to 5, so that's the polynomial order, there is no closed form solution to the roots of a polynomial. Just can't do it. And you can't be creative with it. There are times you can do this, but in general you can't do that with these types of functions. Okay? So that's a bummer, but that does mean that we can find ways around it, because we did find ways around that before with iteration schemes. And in fact, that is really what this is saying. There's just no direct methods, unlike AX equals B, where you can just find the solution. We have to use iteration techniques for this. Okay? And the iteration hopefully will converge to the thing we want. Okay? So that's an important point. The reason we're going to come up with this somewhat complicated scheme is that we know that this problem is hard enough that it has to have an iteration scheme inside of it somewhere. Okay? And where we're going to put that is going to be important. But let's see what we're going to do. We're going to find the sure factorization. That's the end goal. We're not going to go there directly. We're going to directly transform A into a Hessenberg matrix. So a Hessenberg matrix is another type of matrix that has zeros below the first subdiagonal. Okay, so it's not upper triangular. It has one more diagonal below the main diagonal that is non-zero. So the reason why we do that is that we can actually directly transform A into a Hessenberg matrix. That's not so hard of a thing, and we're going to do that just by not iterating, but directly transforming A, using householder transformations, again, and reflectors, because that's what they did with a slight modification. After that's done, so this is somewhat easy, then we're going to use an iterative method to remove that subdiagonal. Okay? So that's the two steps in the process to get to the sure factorization. First, we create a Hessenberg matrix. Second, we get rid of that last diagonal that we don't want, and then we read off the eigenvalues off the diagonal. Okay. So let's go through this a little bit pictorially. So we have this matrix, has a bunch of values, non-zero values. Could be zeros in here, don't really care. We're going to have some transformation determined by Q. Okay, and those are going to be looking like householder reflectors. And we want the zeros below the subdiagonal to be created. And the rest of it, we kind of want to leave alone as we go down, because we want to create the Hessenberg matrix here. So that's the operations for the Hessenberg matrix. And we know that, oh, I got off the bottom of the screen. 1 second, let me blow this up. So we know a lot of things about this. We know basically that instead of actually zeroing out all the way up to the diagonal, that we can actually just zero out the things below it. That's a very minor modification of our QR factorization method from before. I guess that was actually on my screen, not so much because it's broken. So we're going to kind of focus ourselves a little bit just because it gets a little simpler to think about. So we're going to say that A is Hermitian, or it is equal to its conjugate transpose. That just means it's symmetric in the real world. And in that case, Hessenberg matrices are tridiagonal. That's what they're going to end up being, and that's just a nature of you're zeroing out below the diagonal. That means you're going to symmetrically going to be zeroing out the other one. We can completely, of course, generalize this, but this will allow us to say some things and some properties. All the properties we're going to say can be extended to more general matrices. This just makes it a little easier to avoid some of the pitfalls. So where are we going to go? Well, hopefully you've heard of this before, but we're going to put it together in a particular way. The Rayleigh quotient, okay, that's a relationship between the eigenvectors and the eigenvalues. So we're going to use that function, and I'll remind you where that comes from. And we're going to use something called inverse iteration or power iteration to do this. And this is going to form the iteration aspect of our method, or there's going to be tools in our iteration. So let's go through this. The Rayleigh quotient itself, this is it. It's a function. It is x transpose ax, x transpose x. Okay? So this thing can take any vector, but if you look at this, if you plug in lambda, or excuse me, if you plug in an eigenvector of the matrix A into the Rayleigh quotient, you get an eigenvalue back out. Okay? And that's just, if you multiply this is going to be lambda, and everything ends up working out because you get x transpose x divided by x transpose x. So that's just the nature of it. So how are we going to use this? Well, first of all, let's talk a little bit where this comes from. So there's lots of ways to actually derive this. You can actually get it from just considering the eigenvalue problem in the first place. But this is a nice way to look at it, and this is useful kind of more generally. We can look at it more as a variational problem. So instead of trying to find ax and lambda x, we can term it as a minimization problem. So that's really what we're talking about. So this minimization problem says, if I have x, it's an eigenvector, what alpha is going to minimize this thing? We know if this is minimized, that's an eigenvalue, right? So if this is an eigenvector, then alpha will be an eigenvalue if this is minimized. It's going to be 0 in the L2 set. So this is the normal Euclidean distance. You can use different ones, but this gives you the nice way to come up with the Rayleigh quotient. You can also just say, well, if I have a given x, what looks like an eigenvalue, mostly like A, but that's a little bit of a different problem because in that case, we don't actually have a real eigenvector of the matrix A, and we won't get a minimization, but we can ask that question too. But let's look at this. So we know how to solve these types of problems. This is a least squares problem. So if we actually look at it like that, we can take x and treat it like the matrix. We can form this. So now it's x transpose x is going to be our matrix that we were using before. Alphas are known, and this is going to be the right-hand side. So it's a little bit of a strange least squares problem, but we know this actually minimizes that L2 norm. So that if I just rewrite this, then of course I get back out alpha equal x transpose ax over x transpose x. So the Rayleigh quotient again. So the Rayleigh quotient really is actually an L2 minimization problem that's trying to find the value, so a value of alpha, that most closely resembles an eigenvalue compared to the eigenvector you put in. Okay? All right, so that's the Rayleigh quotient, which is great, but that's not going to help us, because it does assume that you either have an eigenvector or you have an eigenvalue. In fact, an eigenvalue wouldn't even do you very good, because you still have to solve this problem of finding the x. But if we had a guess for one of those things, we put the guess in here. In particular, if you had a guess for an eigenvector, you can put it in here and get a guess for the eigenvalue back out. And then you solve an eigenvalue problem. So you have to get an eigenvalue guess that's better than the one you've already got. And then you can find an eigenvector of that thing and then go back through here. So that's the iteration scheme we're going to use, or one of the most basic ones, where you continually have guesses of the eigenvectors to get a guess for the eigenvalue and vice versa. Okay, so that's the first part of our iteration scheme. But we still need to have a way to estimate the eigenvalue, and that's where power iteration comes in, and eventually inverse iteration. So we're going to look at a sequence of matrix multiplications. Those multiplications are going to be a special multiplication, namely powers of A. So this is a normalized vector, right? Whatever x is, it's normalized by itself. And I continue to do that. I'm just replacing A with higher and higher powers. Okay? So what's happening? Like what benefit would this happen? Well, it's going to converge to the eigenvector. Now, why is this? That's a little bit more complicated, but let's look at it. Oh, by the way, this is actually, it's not quite a Krylov subspace, but that's where this is starting to head. So if you know what that is, you can think in those cases. We unfortunately won't cover Krylov subspace methods, so we just don't have time. They will be covered in 4301 if you are interested in other classes. But let's look at this a little bit. Okay, so we have some initial guess. Vector v, 0, so that's going to be our iteration count. Vector v can be written as a linear combination of some basis set of vectors. And we're going to say that in this case, the eigenvectors are nice. They're actually orthonormal eigenvectors. So we have kind of a nice complete eigenspace. This isn't always the case. This is only nice for the matrices we're considering. If we multiply this initial guess v by a, okay, and we're assuming v has been normalized already, so we don't want to have to carry around those. We multiply it by a, we get the a carrying in to the multiplications, and because we know these q's are the eigenvectors, we know that those turn in the eigenvalues. Okay? And I get some kind of arbitrary constants here, so C1 and A1. So somewhere in here is my answer, but it's not quite apparent where that answer is going to come out of. But if I keep on doing this, if I keep on multiplying A more and more and more, it means actually I'm going to get a to the kth power. So k, again, is the iteration count here. What's going to happen is that the lambdas, the eigenvalues, are going to start to grow. And I've actually, should have said this before, we're going to assume these are ordered. So lambda 1 is the greatest, the eigenvalue, and they're fairly well separated, otherwise we also run into problems. But the key component there is that if I factor out this lambda 1k, I get some numbers, but now I'm going to be dividing something that's bigger than all the eigenvalues, and it's growing because it has a power to the kth, k there. Okay? So what's happening by multiplying by this arbitrary vector, a bunch of times, is that the eigenvalues are going to actually be growing, and the biggest one is going to be growing faster than all the rest. So this is going to allow me to pick out exactly the first eigenvalue, the largest eigenvalue. Okay? So if you do this as k goes to infinity, of course, you're going to get back out lambda 1 to the k infinity power, which is not good. But we of course, don't go to infinity. We'll stop at some arbitrary value. Okay? The reason why we care about how far apart these are, of course, is that the convergence rate is going to depend on the ratios of these things. So as those ratios get closer and closer to 1, we get into trouble, and it's exactly why we actually have to assume a simple eigenvalue for these things. Otherwise, we can run into trouble. We have to know that beforehand. Okay, so we found the maximum eigenvalue. We can also find the minimum eigenvalue by doing inverse iteration. This is also sometimes called shifted inverse iteration. This just means that we're going to take the matrix A and modify it so that whatever eigenvalue we're multiplying out of it is going to have the largest value. So it's power iteration, but with shifted eigenvalues. So we pick whatever this mu is, so we have to have some idea where the eigenvalue is. Sometimes you can just actually guess this. It's a little bit less than the eigenvalue you've already found. You shift it, you take the inverse of it, which means that you're going to get, through the power iteration, something, well, I don't have that on the side. You get something that acts exactly like this, except now you're going to have on the bottom that shifted eigenvalue. And you know mu, so you can actually get back out exactly what the eigenvalue it is. So you can do this for every single eigenvalue very slowly. This does not converge particularly fast, but it does work. Okay, so this is called something called Rayleigh quotient iteration. So if we combine these two like algorithms, we first compute the Rayleigh quotient and find an estimate for lambda. So we need to know have some guess of lambda. That becomes the mu, that shift that we're going to use. We have to have some guess, initial guess for the eigenvector. So say the eigenvector in the x direction. That could be a good guess. Find the lambda. Then you do one step of inverse iteration, or you can do a few steps of inverse iteration, get an approximation to the xj, because if you know the eigenvalues like that, you can find the xj's back out of that. And then you rinse and repeat. So you go back and forth between these two steps. You find an eigenvector approximation, and then you find an eigenvalue approximation, and you go back and forth. Okay? So that's Rayleigh quotient iteration. Again, you'd probably want to do this on a matrix that had lots of zeros in it. So our Hessenberg matrix would work for that. Okay, so let's actually write this up, just make sure it does actually work. So give it a whirl. Try to actually just construct this thing. It is just an iteration between these two things, getting back out v and lambda. And we can look a little bit at the convergence rate we're going to see from this in this case. And we're not going to actually stick this in the Hessenberg form. We're actually just going to do the Rayleigh quotient iteration in this case. So give it a whirl. We know the eigenvalues of this matrix already, so we can compare and figure out what happens. So I'll give you a few minutes for that. Okay, so the first thing we're going to do is pick an eigenvector guess. In the notes, I did 1, 1, 1. The reason why we actually start with the eigenvector is that it's a little bit less critical. You get a good initial guess. You do want to be careful. Picking one of the unit vectors can be slightly dangerous. Usually it works, but just be aware that that can happen. So we're going to start with that. And then we're keeping track of the convergence, so we're going to be putting these things in vectors. So want to be careful of that. Okay. What was I doing? Oh. Okay, so that's just computing the initial